Yeah, good morning, everybody. Welcome to the fourth day of the meeting. So, still the first part of the meeting continues today with wave function-based method. And Alok Shukla of IIT Bombay is going to talk to us about this. Uh, can we have this screen, please? Because he's going to tell us about configuration interaction approach and its application to calculate the optical absorption spectra of finite systems. So with that, I hand you over to Alok Shukla. Can you hear me, Alok?
Yeah,
Yeah, please start.
okay. I'll go to the full screen mode. Okay, so you already know the title of my talk, that basically it's about configuration interaction approach, and it can be used to apply to study any property of a molecular system or molecule, quantum dot, or any electronic system basically. Okay, but here I'll focus mostly on calculating the optical absorption spectra. Okay, so let's quickly go into the outline of the talk. I'll give a brief introduction to the topic. Then I'll talk about various electron correlation approaches which are available. Then I'll go and there I'll discuss CI approach in general. And then I will talk about the application of one of the CI methods, namely multi-referencing double CI method, to the problems listed here: long ACs, graphene quantum dots, and B12 clusters. And in the end, I'll have a small slide on summary and outlook. Okay, so let's start. Okay, so I have been working on this for more than 20 years now, so I've had a lot of collaborators. So let me acknowledge them. In the past, Priya Soni was my PhD student, Sridhar Sahu, Himanshu Chakravarti, Praveen Shinde, Tista Basak, Deepak Rai, Preetam Bhattacharya, who will be giving the last talk today. And then at present, I have ongoing collaboration with Sumit Mazumdar, Vikram Mahamia, who recently defended his PhD and now is continuing as an institute postdoc, Rupali Jindal and Arifa, both of whom are participating in the conference. And Arifa, I believe, is physically present there. Okay, and I would like to, before starting, I would like to apologize for not being physically present there, but there were some unavoidable reasons for that. Plus, our teaching is also going on for the first year courses. So, let us start with the introduction. So, inclusion of electron correlations, as we know, is a major challenge in quantum and electron theory. So, normally, what we do is that we start the calculations at some mean field level, and that mean field could be Hartree-Fock or one of the density function theory variants. Okay, if correlations are weak, then mean field approach may be good enough. Okay, and then we just end the story right there. But whenever the correlations are strong in the ground state, then one definitely has to go beyond the mean field. And moreover, even in weakly correlated systems, when we say weakly correlated, we mean that the ground state is weakly correlated. But because the mean field is designed with the ground state in mind, so for excited states, we do have to take electron correlation effects into account. Otherwise, we will not get a good description. And we all know that the treatment of correlation effects is difficult because of the number of degrees of freedoms involved. The size of the Hilbert space increases exponentially with the increasing number of electrons. For bulk systems, the situation almost looks hopeless, okay, because we have an infinite number of electrons. Okay, so therefore, bulk systems are often modeled as finite systems, and we just apply periodic boundary conditions on those. Uh, in this particular talk, I'll restrict myself to finite systems, and if I get the time, then I will talk about how to extend this approach also to infinite systems, that is periodic solids, particularly for the ground states. Okay. By the way, how much time I'm supposed to devote to the talk, and then how much time for discussion? Okay, so I'll continue. Okay, so there are different kind of
About
yes.
1 hour for the talk,
Okay.
and we leave the last 15 minutes for questions.
Okay, so I'll continue till 10:30.
Approximately.
Okay, so there are various electron correlation approaches available. One of the approaches which many of you would have heard of is Monte Carlo approach. So here we can perform random walk in the Hilbert space, and then we can do importance sampling using the Metropolis algorithm. But Monte Carlo approach for the electronic systems has this famous fermionic sign problem, which which can be a major issue. Okay, and the other thing is that it's a one-shot approach. You cannot systematically improve it. Okay, and the calculation of excited states, particularly if the excited states are of the same symmetry as the ground state, is quite difficult. Okay, then we have also Green's function approach, which is very elegant. Okay, here you just go for the things you want to calculate. Okay, and you need not really go get into the nitty gritty of calculating the many particle wave function. Okay, so we define a vacuum, and with respect to that we have virtual excitations. We have something similar, by the way, in configuration interaction method also. Okay, and but the thing is that for Green's function, most of the implementations are perturbative. Okay, so if the perturbation term is not small, then you run into problems. Okay, and it's also based on Feynman diagrams. Okay, so for strongly correlated systems, one runs into difficulties with such a perturbative approach. Then we also have many body perturbation theory. Okay, there we look at the total many electron wave function and correct it for the electron correlation effects. Okay, so for as far as many body perturbation theory is concerned, you can have both diagrammatic as well as non-diagrammatic approaches. Okay, so diagrammatic approach is very similar to the Green's function diagrams. Okay, and but the thing is that beyond the second order, the terms begin to proliferate. Okay, and higher order perturbations, that is third, fourth, fifth, become truly intractable. Okay, and the other thing is that convergence is not necessarily guaranteed. Okay, so you may calculate, and some people have done studies of many body perturbation theory by looking at very high orders, and they see that in some orders there's a singularity, and then in another higher order there's a negative singularity, and then there is cancellation and all that. So the convergence is not systematic. Okay, so many body, and the other problem with many body perturbation theory is that it is not a variational approach. Okay, so the ground state, the fact that we want the ground state by its very definition is the minimum energy state. Okay, so those things. So if this is approach is not variational, you could even go below the minimum energy state. Okay. Before going any further, let me introduce a second quantized notation, because at least in the context of coupled cluster theory, I'll be using it. So I'll just state the main results. If you have a Hamiltonian which has just one and two particle interactions, and it's uh, let's say made up of electrons or any fermionic operator, then the Hamiltonian can be written as what is given here on the board. So first term is the one electron part, and the second term is the two electron part, two electron or two body part. Okay, so right now I am keeping it general, but then I'll talk about the systems that we are interested in. And Fij and Uijkl are called one and two electron or matrix elements or integrals respectively. Okay, and Fij is very straightforwardly defined, and it has, if you have n number of basis functions, its size will be n square. But the two electron integral, that is Uijkl, can, first of all, it can be tedious to calculate, and the second thing is that the numbers of these integrals proliferate, because then we have four indices here, so in principle we will have n to the power 4. Okay, and then there's a step involved in transformation from the basis set, that is atomic orbital, to molecular orbital, and then there is overhead of n to the power 5. Okay, so this can be problematic, but then we have to, that's the way it goes. Okay, and for our kind of systems, atomic, molecular, condensed matter systems, the one electron term is nothing but the kinetic energy part of an electron, and again the nuclear electron nuclear attraction. So if we perform summation over all the nuclei, this is the I mean electron, the attractive force or the attractive potential felt by a single electron. And we all know that the two electron part for our electronic problem is nothing but the electron repulsion potential energy, which is E square over R12. Okay, so let me go having introduced the second quantized notation. Okay, okay, maybe I'll talk about what these creation and annihilation operators mean next. Okay, but I think you may be having some idea already. Okay, so another very popular electron correlation approach is the coupled cluster approach, which has many attractive properties. Okay, it's a very powerful and widely used. All the computer programs have implemented some, I mean, coupled cluster approach to different orders and approximations. Okay, and it's a very powerful, size consistent approach used for taking into account the electron correlation effects. Here it is based upon a exponential ansatz. That is, if psi naught is your reference wave function for the vacuum, okay, which could be your DFT wave function or Hartree-Fock wave function, then you say that the exact wave function will be given by this ansatz, that is e to the power t exponential, okay, e to the power t applying on your vacuum, okay. And so here psi is related to phi naught by a non-unitary transformation. Okay, if we had e to the power it, then it will be unitary transformation. So here we have a non-unitary transformation. Okay, and this t operator is called the cluster operator, and this can be written as a, if suppose we have n number of electrons in the system, it can have T1, T2 all the way up to Tn terms. Okay, and what are these cluster operators? So T1 is nothing but a one electron operator. So we have an annihilation operator for the ith molecular orbital, okay, or the electron residing in the ith molecular orbital, okay, and we destroy it from there, okay, and promote it to a different unoccupied molecular orbital. So that is what the creation operator does. So AI destroys the electron, okay, annihilates the electron in the ith occupied molecular orbital, and A dagger A, now here A is also the subscript and A is also the quantity. So A dagger A is basically creating an electron in the eighth virtual orbit. Okay, so Ij are for occupied orbitals and Ab are for virtual orbitals. Then T2 is, so T1 is creating a single one particle excitation with respect to psi naught. When it acts on psi naught, you get a singly excited state, single virtual excitation. Likewise, T2 creates double excitations. It okay, here I have a it should be AI and AJ, okay, and then we have the corresponding cluster amplitudes. So here in T2, two electrons are being annihilated from the orbitals I and J and being promoted to unoccupied orbitals A and B. Okay, and the strength of this is given by the cluster amplitudes. So in the first case, the cluster amplitude is TIA, and the second case TIJAB, and likewise. Okay, you can generalize it to all the way up to N excitations. Okay, so IJK, like I said, are whole indices, and ABC are the particle indices. I whole meaning occupied orbitals and particle meaning unoccupied. Okay, so if we write down the Schrodinger equation in terms of this ansatz, then we trivially get this effective Schrodinger equation. That is, instead of h psi equal to e psi, we can write it as e to the power minus t h e to the power t, acting on a reference wave function, is equal to e psi naught. Okay, and the noteworthy point is that, okay, and in real life, of course, we cannot have all the n excitations. Suppose we have 100 electrons in the system, we cannot include t 100 term. Okay, so normally we restrict this to 1, 2, and in most of the cases, in some cases, up to 3. But we rarely go beyond that. So I'll talk about what are those called, those approximations called. Okay, so most of the time the scenario is like this: t is equal to t1 plus t2, and I have put t3 in parentheses because in 99% of the cases t3 is included perturbatively, not in the same way as T1 and T2 are determined. Okay, so if we restrict ourselves to 1 and 2 only, then the approach is called coupled cluster singles and doubles. So that means we will have only up to 2 particle excitation operators. And for L equal to 3, naturally it will be called CCSDT, coupled cluster singles, doubles, and triples. Okay. The, I mean, one can, for closed shell systems, that is when psi naught is a unique vacuum, okay, one can develop a diagrammatic expansion of coupled cluster equations, okay, and but in case of strong correlations and near degeneracies, psi naught may not be, your vacuum may not be a single configuration, you may require configuration mixing. So if you have a vacuum which is a linear combination of various configurations, then there is an approach available, coupled cluster variant, which is called multi-reference coupled cluster. So there, if you have chosen m configurations in your vacuum, okay, then you create virtual excitations from all those. Okay, this is something very similar to what I discussed. That is multi-reference singles doubles CI. Okay, but if we move on to multi-reference systems, then in the most general case, we don't have any diagrammatic interpretation. Okay, and so we have to just work with algebraic equations. For excited states, there's a nice version of coupled cluster available that is called equation of motion coupled cluster. So there you basically take, instead of true Hamiltonian, you take this H bar, which is related to the true Hamiltonian by this non-unitary transformation. So H bar becomes a non-Hermitian matrix, while we know that true Hamiltonian by definition is Hermitian. So we take this e to the power minus t h e to the power t operator, which occurred earlier here. Okay, so that becomes our effective Hamiltonian. Okay, and then we just diagonalize that. Okay, but then it becomes a non-Hermitian diagonalization problem. Okay, so but EOMCC is generally more computationally expensive as compared to, say, configuration interaction, which I'll talk about later. But it has been implemented and it's widely available in Gaussian and various other computer programs. Okay, so the pros and cons of coupled cluster. Okay, coupled cluster approaches are size consistent. So particularly when molecules are close to dissociation limit, this is a very attractive property to have. Okay, the cons are that it is computationally tedious and non-variational. So in other words, there's no lower bound on the ground state energy. You could even go below the true ground state energy. It's like MVPT. So now let us come to the main topic of the talk today, that is configuration interaction. So how is coupled cluster different from, how is configuration interaction different from coupled cluster? So for the time being, I'll just use the same terminology of coupled cluster. So in configuration interaction, what we do is that we relax the constraint of mean field, okay, and we allow configuration mixing in the many particle wave function, just like in case of coupled cluster approach. Okay, and but the configuration mixing is of linear type. So if we write the configuration mixing in terms of the same cluster operator t, then the ansatz is not e to the power t, okay, which we had there, but rather a linear ansatz. So t naught is just a numerical term, which will be the coefficient of psi naught in the correlated wave function, and t1, t2, and t3 are the cluster operators. So t1 when applies on psi naught will create single excitations, t2 will create double, t3 will create triples, and so on and so forth. Okay, so the wave function, many particle wave function, has a form now. I mean, if we just substitute the expressions for T1, T2, and T3, then it is, like I said, it is, I mean, the dominant term will be the mean field term. Well, that also remains to be seen. In case the correlations are strong, then mean field will no longer be dominant. But the first term is the mean field term. The second term is the single excitations. Okay. The third term is double excitations, and so on and so forth. You can decide where you want to do the truncation. Okay, at which for reasonably sized systems, it has been possible to include up to quadruple excitations. Okay, but I'll talk about it later. Now, although in this expression, I have used the same notations as for couple cluster, but the cluster amplitudes now will not be, because this is a different approach. So cluster amplitudes will be determined by solving a different set of equations. Okay, and let us examine what those equations are. Okay, they will not be solved by, I mean, by the algebraic equations that you end up with the couple cluster theory. But before I go into it any further, let me just give a like a diagrammatic interpretation or a diagrammatic pictorial representation of the mean field. Okay, for a closed shell system. Okay, for so all the molecular orbitals are doubly occupied in the ground state as per of Bow principle. Okay, so let us say that some closed shell system has this many. Okay, so I have not specified how many orbitals are there. Okay, so EF gives us the location of Fermi level. Okay, and because we have a discrete system and a closed shell system, so there will always be gaps. Okay, so depending upon the number of electrons you have, a certain number of orbitals will be doubly occupied in psi naught, while all orbitals above it will be unoccupied. Okay, so these are my ij indices, and the unoccupied orbitals correspond to AB indices in the language of the cluster amplitudes. Okay, or the occupied orbitals are the whole orbitals, and the unoccupied orbitals are the electron orbitals. Okay, so you can, or if you want to go to the band representation, then the occupied orbitals are the valence band, and the unoccupied orbitals are the conduction band. Okay, that will be true for the case of solid. Okay, and then what happens is that there are core orbitals or significantly lower energy orbitals as compared to the ones which are close to the Fermi surface. So, I mean, we can create an effective Hamiltonian by freezing the orbitals which are far away from Fermi level on the occupied side. Okay, and we get one electron effective potential for that. Okay, and we can delete the virtual orbitals by just throwing them away, which are also very far away from the Fermi level, because most of the action will be should be close to the Fermi level. Okay, most of the particle hole excitations should be close to the Fermi level. So this is freedom which we have in basically all the approaches, but I'm mentioning it in the context of configuration interaction. Okay, so we freeze orbitals, particularly the core orbitals, and delete the high energy virtual orbitals. Okay, so above pi IA, that is a singly excited configuration, doubly excited configuration, etc., denote slated determinants, or they may denote in, I mean, if you are imposing at right from the outset, if you are imposing the angular momentum symmetry, that is the spin symmetry, then they could be also configuration state functions, CSFs. Okay, and they form these phi naught coupled with all the excited determinants, that is singly excited, doubly excited, triply excited. They now form the basis of the many particle Hilbert space. And it is up to me to decide which of these excitations I am going to include by suitably deciding. Okay, uh, in some problems, we may need just up to doubly excited determinants and things of that type. So in case of configuration interaction, like I mentioned, my ansatz is linear. So here I have, now I am using a more compact notation. Pi I are any one of these basis functions of the many particle Hilbert space. That is, it could be psi naught or any one of these excited determinants. And the corresponding Ci is a is a coefficient which needs to be determined by, and in case of Ci, it will be determined by variational principle. Okay, so in case of coupled cluster, I repeat that the expression was nonlinear because of the exponential ansatz, but here everything is linear. So I just apply Lagrange undetermined multiplier approach. Okay, I vary these coefficients. So Ci's are now my variational coefficients. I vary these coefficients because my basis functions are fixed. Okay, I vary these coefficients so as to minimize the total energy. Okay, so again, because I am minimizing the total energy, so it's a ground state approach. Okay, subject to the normalization constraint, and E is my Lagrange multiplier, which imposes that. And if I go through this, then I will get an eigenvalue problem, which will be of the form H tilde, where H tilde denotes the matrix corresponding to the Hamiltonian with respect to the given basis. C tilde are the column vectors, are basically the coefficient Ci arranged in the column vector form. E is the energy that we are looking for, and C tilde. So it's a simple eigenvalue problem. Now let us examine what is H tilde. H tilde is nothing but the matrix representation of my Hamiltonian with respect to the chosen basis in the Hilbert space. Okay, which is totally under my control. I decide how many of phi i's do I include in my Hilbert space basis. Okay, and although the theory is based on variational principle, that means ground state is guaranteed to have a lower bound. Okay, I mean it will never go below the true ground state value. Okay, but there's something very attractive here, that suppose I have m uh, configurations. That is, I is from 1 to m. So H tilde will be a n cross m matrix. Okay, and if I diagonalize this H tilde, then I get m eigenvalues and m eigenvectors. Now the lowest of these I interpret as the ground state, but the higher ones I can interpret as excited state. Okay, so that is the beauty of configuration interaction approach, that you can get not just the ground state but also excited states, which are needed if you want to calculate operative properties, linear or non-linear and things of that type. Okay, so this is the attractive part of it. But computationally intensive parts of CI approach are basically construction of the Hamiltonian matrix with respect to the configuration basis. Okay, then depending upon how many configurations you have included, that is how large is m, you diagonalize H tilde. Okay, so if it is 100 by 100, then you can obtain all the eigenvalues and eigenfunctions, or even up to a few thousands. But if it runs into millions, then obviously you cannot do that. But fortunately, we have we have to obtain solutions of only a few low-lying excited states to say something about optical and other properties. I mean, if we had to obtain all the excited states, then the situation will be truly hopeless. Okay, so we can work with M, very large configuration basis, which can even be into billions. But you cannot obtain billion eigenvalues and eigenvectors. You can obtain, say, 10, 15, 20, that sort of thing. Okay. So there are, in quantum chemistry in particular, there are efficient algorithms which available to construct H tilde, that is a Hamiltonian matrix, and also for diagonalizing it. Okay, for diagonalization, Davidson algorithm is there, or Langzos is there. Okay, so construction of H tilde involves another step where we transform the 1 and 2 electron integrals from the AO atomic orbital representation to molecular orbital representation, so that makes it an n to the power 5 problem, and then diagonalization has its own overhead. So typically CI approach scales as n to the power 6. Okay, So choosing a large basis, choosing a basis, compact basis is very important in all the approaches. Okay. So for large M, diagonalization, like I said, becomes computer intensive. And but if we are restricting ourselves to only a few low-lying routes, then it can be done efficiently, even for millions and in some cases billions of configurations. Okay, so like I said earlier, that in one CI calculation, you can obtain not just the ground state but also low-lying excited states, which you may need in case you want to calculate optical properties. Okay, and the other eigenfunctions, like I said, not just the optical. I excited states can be used to calculate other properties also, but my focus is on optical properties. Okay, for optical properties, we know that we normally use the. You must have students in particular must have studied it in their quantum mechanics course or atomic and molecular physics course, that we normally calculate optical properties using the electric dipole approximation. So we need to calculate transition dipole matrix elements between these eigenfunctions. So that is also somewhat tedious, but not as tedious as calculating the two electron matrix elements, because the dipole operator is the one electron operator. Okay, if it is possible to perform full CI calculations. Full CI means that you have considered all excitations. So if you have any electrons, you have included up to t to the power n terms. Okay, so then you get the full CI. So it is possible for some model Hamiltonians. It has been possible to go up to 18 electron systems or 20 electron systems, but not much larger than that. Okay, because as you can imagine that FCI full CI approach will lead to huge matrices, and it will basically override all the hard disks. If the problem is huge. Okay, so it can be used only up in a limited number of systems. Okay, so that means we need to have some kind of a systematic approach for carrying out the truncated CI expansions. Okay, so truncation schemes are in a sense similar to the coupled cluster method. Okay, so you basically truncate, decide up to how many excitations do you want to calculate. Okay, so if you, in some cases, as a zero order approximation, even single CI may be sufficient, and that can be done very trivially. Okay, so if you are restricting yourself only to the psi naught and singly excited determinants, then the approach is called single CI, SCI, and some people call it CI single. So, for example, in Gaussian, it is called CIS. Then you have, if you want to include singles and double excitations, then it is called SDCI. Then likewise single, double, triple. Okay, SDTCI, SDTQCI, or simply quadruple CI. Okay, so all those truncation schemes are available. Okay, the advantages of CI is that it's a linear approach, conceptually simple, and also variational in nature. So your ground state energy is never going to go below the true ground state. Okay. The disadvantage is that truncated CI expansions are not size consistent. So you don't want to use this approach on a system which is near about to dissociate. Okay. Because then size consistency becomes important even for the excited states. Okay. So fragmentation processes naturally cannot be properly described. Extrapolation from smaller to larger systems then becomes unreliable. Lack of size consistency is not a serious problem for low-lying excited states, particularly if the molecule is in its normal state, not near the fragmentation limit. Okay, and for optical absorption, linear and both linear and non-linear, because I have used it, so I know that, and I keep on comparing our results with the experimental ones. So I have found it to be very reliable. Okay, then let us go beyond singles. The CI which I have discussed so far, because there I used a single vacuum, single configuration, phi naught as a vacuum. But again, we can have a situation where due to stronger correlations or accidental degeneracies, Okay, and sometimes the nature of excited states is such that you need to have two configurations are totally degenerate. Okay, and then you need to include both of them, because if you include one of them, then you are not going to get good description. So in that case, we need to generalize and come up with the multi-reference CI. But multi-reference CI approach is very simple. Okay, you decide your now your trial vacuum or starting vacuum becomes a linear combination of configurations. Let's say m of them. Okay, and you then you have to consider all the virtual excitations, that is singles, doubles, whatever, okay, from all of those. And sometimes when you calculate, we have multiple configurations, you may get duplicate configurations. So your computer program has to be smart enough to rule out the duplicate configurations and come up with a CI expansion for the multi-reference case. Okay, a very popular representation and actually quite tractable also is multi-reference singles and double CI. That is, you choose your references and then only consider single and double excitations. But now, because you are allowed to choose, you can consider your some of the references will already be virtually excited determinants. So by applying singles and double excitation operators, you can get higher order operators, okay, configurations, triply, quadruply, depending upon how smartly you choose the reference wave functions. Okay, so in MRSDCI, we, like I said, we include the single and double excitations from all the reference wave functions. Okay, so this set can be systematically expanded. Okay, to include to describe both the ground and excited states, and how to construct your reference wave functions. You can take them as not as linear combinations. You can take them independently and just create a configuration set, construct H tilde and be done with it. Or you can create a linear combination of these. Okay, and in that case, you have what is called a contracted multi-reference CI. Okay, and in contractions, like I said, that your reference wave function is can be a linear combination of individual configurations. So you can reduce the CI matrix dimension that way, but the computation and the diagonalization part of the of the entire problem will be easier because you have a smaller matrix to diagonalize. But on the other hand, you will have to do more work in constructing the matrix elements. Okay, so having discussed that, and let me see how I am doing on time. So it's 10:08. I have a few more minutes. Okay, so we have used in our group multi-reference singles double CI approach, MRSDCI, to study optical properties of polymers, graphene quantum dots, and also clusters. Okay, and we have applied it to study both linear and non-linear optical processes. But here the examples which I'll be discussing will be this linear optics, because non-linear optics becomes more complicated. And we have used it with model Hamiltonians like PPP, meaning Parikja Popal, CNDO, Indo, etc. And also we have used it for ab initio approaches, particularly for clusters. Okay. And what I did is that I found a package called MELD, written by Ernie Davidson of Indiana University, very efficiently written package in Fortran 77, which is modular. So it is split into many parts. So you can pick and choose which part you want to choose. Okay, and so, for example, if I'm not doing ab initio theory, I'm doing PPP model calculations. So I do Hartree Fock, etc. calculations using my own code, and then supply that one and two electron integral to MELD, and I'll ask MELD to do the remaining problem. Okay, so uh, for example, I mean, just to continue with that, PPP model, Parisa Focal model was, I'll be discussing it in somewhat greater detail later on, was designed to study the optical properties of planar pi conjugated systems. Okay, only in planar systems you have sigma pi separation. Okay, so we wrote a code in collaboration with my PhD student, a Fortran 90 program which does the Hartree-Fock calculations for PPP Hamiltonian, and also does various other things, that is transforms from AO to MO representation, and makes everything ready for MRSDCI calculations to be done by the MELT package. Okay, so for optical properties of clusters, we have used a fully ab initio approach, where we use Gaussian basis functions, and MELT package is capable of doing that also. So then we don't need to use my PPP program. We can just use MELT package in its entirety, okay, and then choose whatever type of CI diagonalization, I mean CI approximation I want to use. And the MELT package is good in the sense that it also has the modules for not just for creating the Hamiltonian matrix and diagonalizing it, but also for computing various properties once you have the many particle wave function available, properties such as transition dipole moments, which we need for calculation of optical properties. Okay, a few examples over the years. Okay, I've been working on it for a very long time. So these are some examples of polymers. So PPB, then phenyl substituted polyacetylens and things of that type, polyacenes. Okay, so let us start now. At this point in time, I am done with all the conceptual things, and I am now going straight into the applications part. And and I will, because I've been asked to give another talk at 2 o'clock. So in the afternoon session also, I will continue with the applications part. Okay, so and whatever time is available, I have 100 something number of slides, but I mean I'll abide by time. Okay, so these are some of the examples of my past calculations, and here the first application which I discuss is a favorite paper of mine. Okay, with the Himanshu, PhD student, okay, Himanshu Chakravarti, and so this had to do with the longer acenes. Okay, we all know about smaller acenes, that when we have a single benzene, two benzene rings, then the material is called naphthalene. When we have three, then it is called anthrazine. When we have four, tetrazine. When we have five, pentacene. Up to pentacene, it's very easy to synthesize these materials, and they are well studied. But beyond pentacene, that is hexacene, heptacene, uh, octacene, and nonacene. Nona meaning nine fused rings. Okay, so I mean, earlier people were not successful in synthesizing anything beyond hexacene. Okay, but there was a paper, and I'll go into that, where they managed to synthesize, a German group. They managed to synthesize both octacene and nonacene. Okay, and they were interested, and they looked at the optical properties of, I mean, measure the optical properties, and they asked us to do these calculations so that they could interpret the results. So this was, although we, I mean, published the paper separately from them, but it was like a collaborative effort. Okay, so I will get into the motivation part. Okay, so the motivation is that if you keep on increasing the length of the acene, see up to hexacene has also been synthesized. It is well known that from hexacene up to hexacene, the ground state is a singlet state. But there was a paper in 1982 by Angliker et al. Who predicted that nonacene, if we keep on increasing size, nonacene will have a triplet ground state. Okay, but their calculations were based only at the single CI level of theory, which, as we know, does not include electron correlation effects in any significant manner. Okay, so the question was whether these calculations are even reliable. Okay, then people have done many calculations using DFT and all that, and people did not agree with this result of Angliker et al. Okay, most of the calculations were predicting that all the way up to nonacene, the ground state was a singlet. Okay, so then these people, another set of people, that is Bettinger et al., approached me, okay, around 2008 or 9, okay. They said that they have synthesized up to, you know, nonacine, octacine. They synthesized octacine and nonacine, okay, and they had measured the optical properties, and they wanted us to calculate the optical properties theoretically and compare it with their results. And perhaps we can interpret whether they have, they are observing a triplet ground state or a singlet ground state to settle this issue once and for all. So when Bettinger asked me to do this, so we decided to, me and Himanshu, so she did the calculations to probe this matter, okay, and using the PPP model. So now that I'm going to get into PPP calculation, so let me give a brief introduction to PPP model, fast-paced introduction. Okay, so all of us will be knowing that there's a model called tight binding model. Okay, so PPP model has three terms in the Hamiltonian. The first is the one electron term, which is also called the hopping, which is there in all the tight binding models. The second term, people from the strongly correlated community will recognize that this is the Hubbard U term. That is when two electrons are on the same side, but the electrons are of opposite spin orientations. Then they feel this Hubbard U repulsion. Okay, and then we also have, so in Hubbard model, you get Hubbard model if you retain the first two terms, but in because PPP model was developed for pi electron systems, so not for d electron systems for which Hubbard model was designed. So electrons are localized, but not that localized. So there is going to be a long range interaction between pi electrons, two pi electrons, and that is given by this Vij term. But that is of density form. This is not the most general electron correlation term, uh, electron repulsion term, but of density form, better than nothing. Okay. And here I am just using the same creation annihilation operator approach which I described earlier, except that now I am here as per the notation, popular notation, instead of calling them AI and AI dagger, I am calling them CI and CI dagger. Okay, and here spin is also, spin orientation up and down are also mentioned explicitly. Okay, and Ni is a number operator for a given spin, and Ni is a total. Unfortunately, I am getting a knock on my door, so let me just quickly mute myself. Okay, so I'm back, and let me get to the full screen. Uh, I'm not getting. How do I suddenly? I'm not able to get to the screen. I see it on the. Uh, Let me stop. Shall I stop presenting and then
Yeah, we shall.
Please stop
represent?
listening.
Yeah,
Restart.
yeah. So are you able to see it now?
Yes, sir, it's open.
Okay.
Yes, it's open now.
Okay. Sorry for the disruption. Uh, let let me just go to the slideshow. Okay, so here we were. So here INJ, like I said, I mean, a PPP model was designed by Pariser, Parr and Popel. So it was basically with chemistry in mind, so pi conjugated materials. And but the terminology is very similar to what the physicists use in the context of Hubbard model. Okay, and the electrons which are involved here are strictly pi electrons. So we assume that sigma pi separation is there. Okay, and sigma electrons are so far away from the Fermi level that they will not contribute to low-lying optically excited states. Okay, so in that approximation, we can reduce the entire problem only to pi electrons. Okay, and we can forget about the remainder of the electrons in the system. So typically, I mean, for pi conjugated materials, for each carbon atom, we get one pi electron. So for normal systems, we get, in the language of Hubbard model, we have a half-filled system. Okay, now this has some parameters here which we need to determine. Okay, and Tij, that is the hopping amplitude. Then what is the value of u, and how do we determine the long range Coulomb interactions? So one uses, I mean, there are various approximation schemes, parameterization schemes, but we have been using, and that is inspired by Sumit Mazumdar's group. I believe he is also there. Okay, so we have been using the so-called Ono approximation, where Rij is the distance between two sites I and j in angstrom units, and 0.6117 is a determined parameter. And we also apply, to take into account the screening effects, we also have a dielectric constant, which is there only for long range part when I is not equal to j. Okay, and the standard parameters which have been in use for a long time are correspond to T equal to 2.4 eV for carbon based pi electrons. Okay, U equal to 11.13 eV, and Professor Ramasesha, who will be giving a talk later on, he has been using slightly different parameters, 11.26. Okay, and Chandros and Mazumdar long back, in the context of phenylene based pi conjugated systems, okay, they saw that if they reduce U to be 8, okay, not take it to be so high, but reduce it to 8, and in addition use a dielectric constant, then they got better results. So we have been using, in our calculations, we have been using both sets of parameters, that is the normal standard parameters as well as Chandros Mazumdar parameters, which we call screen parameters. Okay, and now in order to calculate the optical absorption spectra, we use the sum over states approach. Okay, so sum over states approach gives you the optical absorption spectrum or optical absorption cross section in terms of these quantities. This is a standard textbookish approach. So if you're looking at the optical absorption of nth state, and for n equal to 0, it will correspond to ground state. Okay, but you can also look at the optical absorption spectra of an excited state. So you need to then calculate the transition dipole moments of higher energy states. Okay, the excited states obtained from your CI or whatever calculations. Okay, so this is something which is supplied by the program which you have written. Okay, omega in is the frequency difference between the two states. Okay, and then we have the usual Lorentzian type of line shape, and sum over states is I are the states which are higher than the your state for which you are calculating the optical absorption. Okay, so we have to perform a discrete summation, so that is the essence of sum over states, or SOS. Okay, and here you have to exercise caution. How high do you want to go? Because the higher you want to go, you will have to calculate that many more eigenfunctions and transition dipole moments, but you will get better accuracy. So you have to optimize those things. Okay, so this is the formula which we consistently use for calculating the absorption spectra. which I'll be presenting in this work. Whether it is for PPP model, this is a standard formula which is agnostic to the model in question. So you can use it for any Hamiltonian that you may like. All you need are the reference state and the excited state wave functions, any particle wave functions, and the ability to calculate the transition dipole matrix elements. Okay, and this corresponds to single photon processes, obviously. For two photon absorption, etc., the terms become significantly more complicated. Okay, so in our study, we went, although Bettinger et al. Had considered synthesized only is octacene and nonacene, but we decided to go one length longer. We said that for future, we are also calculating decacene, that is acene with 10 rings. Okay, so that will be a prediction. If someone synthesizes decacene in future, then they can compare their experimental results with our theory. Okay, so one brief thing, by looking at the structure, and if you have some feel for group theory, you will immediately recognize that all the acenes with the uniform bond lengths uh, and uniform bond angles will correspond to D2H point group. Okay, and in principle, the bond lengths and bond angles may be slightly non-uniform, but we also did a calculation of a small non-uniformity, and we saw that the results deviate very little as compared to the uniform bond length. So that is why we have continued with this particular approximation. Okay, so if you have a D2H representation and you are using a planar, you have a planar system and you are using PPP model, then your orbitals will correspond to only, and also your many particle states will correspond to only these four irreducible representations: AG, B2U, B3U, and B1. Okay, the lowest singlet state, if you do the calculations, you will always get it to be singlet AG. Okay, and if it is a ground state, then the principal quantum number is n equal to 1. The lowest triplet state in this representation you obtain by considering the many particle wave function of EG, okay, or the Hartree-Fock reference state, and make it a singly excited determinant, that is, make promote an electron from HOMO to LUMO. Then you can combine the two spins, two open shell configurations, to get a triplet, and it will have the spatial symmetry. You can get a triplet as well as a singlet, and but you will have the spatial symmetry of B2U. Okay, so the question is, can this triplet state go below the singlet state? Okay, that is the question we are going to address. And I think I'll be able to do only partly because I am approaching the time limit. Okay, so first let me give you the details of the calculations. Okay, so we used, the nice thing about MELT package is that you can implement point group symmetry along with the angular momentum symmetry right at the outset. So your configuration state functions will be eigenfunctions of a given point group operator. So that means they will be in classified according to the irreps and also of the spin operator. So for one AG, singlet AG, for this is the total number of configurations. Nref denotes the total number of reference configurations, and N total denotes the total number of configurations in the CI expansion. Okay, so for octacene, we had the maximum number in one singlet AG state. We had close to 800,000. Okay, 7.68 into 10 to the power 5. Okay, then for nonacene, we approached almost, for singlet, we approached almost 1 million. Okay, for decacene, we went beyond 1 million configurations. Okay, and likewise similar information is given for other irreducible representations. Because okay, and for triplet, the configurations, because these are highly open shell configurations, so the total number of configurations for decacene went almost close to 2 million. Okay, but in other calculations we went beyond, we approached 8 9 million also. Okay, And so two types of calculations: standard parameters and screen parameters. Okay. Now it is exactly 10:30. So what should I do? I'll just explain this slide, okay, and then I leave it to the chair of the session to decide, guide me further. So, for example, black ones, we have compared our results on the singlet triplet uh, separation, that is the energy of spin excitations, okay, singlet triplet separation as a function of the length of the acene, okay, and the black ones are for standard parameters and red ones are for screen parameters, and the other ones are some of the calculations which include DMRG PPP from Professor Ramas Sisha's group, and also DMRG calculations using ab initio approaches and the experimental work. Okay, so we see that for all the states, I mean, DFT calculation predicts for longer ACs a very small spin excitation, but none of the calculations are predicting that triplet will become the ground state, because then we will have to have a negative value. Okay, so but our calculations are in very good agreement. They are following the experimental results up to pentacene, up to hexacene. Okay, beyond that, experimental results are not available. Those are predictions, and also they are in good agreement with the electron correlated approaches. So one thing is for sure, our calculations and many other people's calculations predict that up to decacene, we didn't go beyond decacene. Up to decacene, we will have singlet will always be the lowest energy state, and triplet will be roughly zero point 0.5 eV higher for decacene. Okay, so now it is 10:32. So Priya, should I stop now, because we can continue with the remainder of the applications in the afternoon session?
Yeah, exactly. So let's take some. So can we stop now and we take questions now? Is that fine? Can you hear me?
Yeah, I can hear you.
Okay, so can we take questions now?
Yeah, sure.
Okay, thank you for a very nice talk. So now the talk is open for questions. Anybody? Right. Yeah, while we're waiting for them to for the audience to ask questions, I had a couple of points. So one thing is, can you tell us what is the method you use for storing these large, wave functions in this case?
Actually, like I said, that the electron correlation part was done by melt package. So, can you hear me? Hello?
Yeah, we can hear you. Oh.
Okay. Is done by melt package, and melt package was written in the 70s. So at that time, the RAMs of the computers were very tiny. So whatever they had was available on the hard disk, even though hard disks were also nothing compared to what we have now, but still they were better than RAMs. So it is strictly hard disk based. So what I mean, I went into their codes. So what they have done is that they have used direct access files. Okay, so random access. So they have by using random access files, you end up using hard disk as RAM. Okay, so it was all the matrix elements, and also uh, the large configuration wave functions when you're using very like large n. Okay, they were all stored on the hard disk. Okay, and they had a very clever way of approximating uh, the small matrix elements, small numbers. So they were using only 4 bytes, real star 4 for that, and the larger matrix elements where you need more precision, they used real star 8, that is double precision. So it's a very cleverly written program by Davidson Group.
So
It's basically hard disk based.
do the new implementation use something like hashing, or because that can help
Uh-huh.
lots of things.
Yeah,
So
yeah.
maybe if you can give a flavor of this also in your afternoon talk, it would be nice. Like, can you? I mean,
Flavor of what?
yeah, a flavor of, I mean, the if you a flavor of the new methods which are used for storing the wave function and accessing it, like searching and hashing.
Yeah, modern methods.
Yeah, the modern methods.
Modern methods actually these days, you don't need such clever programming. Okay, because the computers, even the laptops have huge RAMs. Earlier in their times, they didn't imagine anything will ever go into gigabytes, but we have RAM of gigabytes. Okay, 8 to 16 gigabytes RAM is available on laptops. Okay, and huge hard disk, terabyte hard disk. So you can just store everything just like that. You don't need to do anything clever. Uh, if I were to rewrite the code, which I keep on thinking about, but so far I didn't find the time. So I will just write everything as such, because there's no point in doing such clever programming. But I am truly impressed with the kind of clever programming. And Professor Ramasesha has been doing something very clever with his DMRG code that he has been using. He has been working at the bits level to represent the skins and things of that type. But bits have also been used to represent the skins in melt code. 1 and 0. Yeah, 1 and 0 up and down.
So how do you, I mean, choose, like, if you have multi-configurations, you spoke about multi-configurations.
Uh-huh.
How do you, like, go about
Yeah.
choosing the
Yeah,
configurations for that?
yeah. So let me go back to, okay. Let me go to the slide mode. It'll be easier to go back. Okay, let us consider any one of these A scene, let's say A scene 8. Okay. So what, for example, for the ground state, the degeneracy, the ground state is non-degenerate. So what we do is that we first take the Hartree-Fock, that is for calculating singlet EG state. We first take the Hartree-Fock state and perform a SDCI calculation, that is singles doubles CI, just single configuration SDCI calculation. Okay, and then we look at the ground state wave function. Now, if it's a weakly correlated system, your Hartree-Fock configuration will be anywhere from 0.8 to 0.9. Okay, and then other configurations, singly excited and doubly excited, could have slightly, it will, the coefficients will be much smaller. So we set a cutoff that I'm going to include those configurations whose coefficient in the SVCI expansion was, say, zero point 0.1 or above. Okay. So in the next calculation, which then becomes MRSVCI calculation, suppose I find one such configuration. Okay. So my MRSVCI calculation will have two configurations. One, the Hartree-Fock, that will remain for the ground state, but then this new configuration which I found. So NREF will become 2, and then I will perform my first MRSVCI calculation, and repeat this procedure again. So it's not highly automated. One could, in principle, automate the whole process. So we have to, perform one CI calculation, then look at the many particle wave function of whatever state you are interested in, for example, the ground state. Okay, and then look at the configurations which are contributing significantly to that, and include those in your reference configuration. And for ground state, the convergence comes very slowly. Very fast. But now, how do I do it for the excited states? Yeah. So for this orientation, that is, if I assume my x-axis to be along the conjugation direction, then if you want to calculate B2U, B3U type of states, which will have the polarization along the length of the acene, okay, so B3U type of states will have this necessarily a double degenerate character, okay, and this has to do with the fact that we are using a bipartite model, nearest neighbor tight binding model, and things of that type, okay. So for example, your two configurations which are contributing equally could be homo to L plus 1 Homo to LUMO is normally for B to U, HOMO to L plus 1, and HOMO minus 1 to L because of the particle hole symmetry. Okay, so you cannot neglect one and keep the other because both are equally important. So in that case, symmetry guides you to start the calculations, and it will be necessarily for B3U, orientation, B3U type of states, it will necessarily be a MRSD CI calculation with two degenerate configurations, and then you proceed as we did in case of. So you first do calculation, excited state calculation with n equal to n ref equal to 2, and then examine the states which are giving rise to a significant peak in the absorption spectrum and include those configurations and so on and so forth until everything converges. So it's an iterative procedure. I wish I could automate it, but then I'll have to do a lot of coding for that, get into this. So I haven't found time for that, but it works. I mean, you can do your calculations in a fairly reasonable amount of time.
Okay, thank you. And there are a few online questions. Anybody? Oh, sorry, one second. There's more offline. One second.
Online questions, can I read them or?
There's one more offline. So,
Uh-huh.
Sir, I have a question. So,
Mhm.
what are the advantages of using this wave function methods in comparison to other excited states method like GW, BSC and all? So, why do you choose to use this method to calculate the excited states rather than those methods?
Rather than which methods? DFT based.
GW, BSC or TDDFT.
Okay.
So, when do I choose this method over other methods?
I choose it because it's very simple to implement. GW, there was a talk yesterday, right? On GW, not yesterday, but on 18th, I believe. Okay, so GW, Manish would have told you that that is also quite tedious. Okay, and you have to calculate the dielectric function and things of that type. So here I don't have to calculate that, but people have applied GW for these. In particular, the group of Steve Louis in University of California, Berkeley, they studied these systems from a perfectly ab initio point of view, and they applied GW in BSc. So it can be done. In my case, because I am using a model Hamiltonian, so for me it is much simpler. So many electron correlation effects which the ab initio people who practice ab initio theory, they have to take into account, they are already accounted for in terms of approximations. Okay, so for me the conceptually simplest way of doing things is by using the configuration interaction. But like I said, I mean, people have applied uh, GW in BSc for these acene and other polymers. Okay.
Okay, thank you.
just one. Are there any more offline? Yeah, there's one more. First, we'll answer the offline ones, and then you can go on the new.
Offline, I should read the comment. Mukesh Singh.
Just one sec. There's one more. Yeah, go ahead.
Nice talk, sir. So the gap calculation I am talking about, so it actually differs from the other calculation, and I want to understand eventually that comes the validation.
I am still,
The gap calculation validation comes into mind. So is there any other perspective or any other calculation so that you can validate the gap?
I am not able to hear you properly.
Okay, he wants to know how do you validate your results, right? I mean,
Yes.
how would you validate the results that you have? What do you cross check?
Okay. I understand the point. Yeah. So when we come to this in the afternoon part, we always validate them against the experiments. So because this story is
But, I
fairly
mean,
incomplete.
the experiments.
Yeah.
But any other theoretical?
Theoretically speaking,
Results you
we
compare.
can do our best. So, for example, for octacene, I am only encouraged by the fact that for for decacene, for which the material has not been synthesized as yet, and we have produced the results. So, I mean, I have hope that our results will be correct simply because they seem to be correct or they are in good agreement with what was seen for octacene and nonacene. Okay. But other than that, you can only do a fairly rigorous calculation, as rigorous as the system will allow you to do, or the resources you have, and then hope for the best. But in our case, I mean, for like pi conjugated materials, a lot of data is available. So that's why this approach, PPP model based approach, and CI approaches are well validated. Okay.
Any more of them? Otherwise, Mukesh, you unmute yourself and ask your question. Having problems unmuting. So, I mean, then Alok, you can just answer the questions which are there.
Mukesh Singh and see, Mukesh Singh is probably my own PhD student, and Khushbu Dange also. Okay, so I see two questions. Let me address Khushbu's question first. Why PPP model can only be applied to the planar systems? I mentioned it right in the beginning that only for the planar systems you can have the sigma and pi separation. Okay, if the system begins to acquire a curvature, okay, it becomes convex or whatever. Okay, then the sigma pi separation, if the curvature is small, then you could still probably apply PPP model. But if the curvature becomes significant, then you have to really question. But there's another system with very significant curvature, but somehow PPP model also works, is C60. C60 and C70. They are like both like. So, but because we have done our own calculations, although I'll not present them here, they are there in a review article. If you choose the parameters properly and argue that your sigma pi separation is valid locally at each point, there's a pi orbital, although it's not flat. So using that approximation, for somehow we got very good results even for C60. But normally it will only, I mean, the model was designed by Parr, Popel, etc., these famous people, for pi conjugated systems, which by definition are planar. Okay, and Mukesh is asking, in Hubbard U plus V improves the band gap. Does PPP model give exact? See, PPP model is a model. Okay, then the question is, at what level do you perform your calculations? Okay, so for example, if your parameters are properly chosen, okay, and you do full CI calculations, then this is the best you can do. If it compares well with the experimental results, then you, I mean, you say that things are going well. Otherwise, you have to change the parameters. This is not ab initio approach. Okay. But then DFT has its own set of approximations. It's a mean field approach. Okay. And you can correct it by applying U and V. So everything is approximation. Okay. So I hope.
Yeah. Thank you very much. And so we look forward to your next session in the afternoon. So we'll break now.
Okay.
Thank you.
So I have to join at 2 o'clock, right? 2 p.m.
2 p.m. Yes.
Okay. Okay. Thank you so much. And thanks for organizing such a nice workshop.
Yes. Okay. Bye.
Yeah. Bye.
Just tell me.